everyone, welcome to the session. So in this particular video, we will talk about another amazing application of divide and conquer module, which is about a quick sort. I'm not sure that how many of you have already been aware about this particular sorting algorithm, but this sorting algorithm is the one which is actually used in real life scenarios whenever there is a actual need of sorting algorithm. What is the meaning of that actual need? Means when your array is almost unsorted. At that point of time, QuickSort is the one which can give you very fast results. Why is that so? That we will see in this particular video. But saying that thing in your head, please focus that whenever your array is almost sorted, that point of time, I am not saying that QuickSort is giving you the good result. That we have already covered up. In that scenario, insertion sort might be the best one to go for, right? So let's get started with the concept of QuickSort algorithm. Again, a very interesting concept in algorithms module. Try to understand this concept very much carefully. So let's get started with the QuickSort algorithm. So now, whenever we are talking about this algorithm, the good thing about this algorithm is where it is doing a smart work is the dividing part, right? So until so far, we have seen that whatsoever applications we have discussed in case of a divide and conquer, the division of an array is happening like finding out the middle value, which we are finding out with the help of I plus j minus I divided by 2, right? Where we are saying that I is the starting index and j is the ending index. And this is how mainly in every application, if you will observe, we are trying to calculate the mid value. But when I'm talking about this QuickSort algorithm, it uses something called as partition algorithm. It uses something called as partition algorithm to divide the array into two halves. So this is something which was happening in other applications, like when we are talking about a merge sort or we are talking about a binary search. This is how we are dividing our array into two halves, can I say? But when we talk about the concept of something called as a quick sort, we came across, or the developers came across, something which we called as a partition algorithm. Very important. And this is the key thing in a QuickSort to understand. Remaining concept is same, but how basically the array is dividing into two halves, which is done by the partition algorithm, is something which I would say is the important thing here to understand. For example, in merge sort, when I was trying to explain to you the merge sort, I told you that merge procedure is something which is really important to understand. Similarly, here I am saying that in this particular partitioning QuickSort, partitioning algorithm is something which is really important to understand. How it is working? Let's try to understand that part. For example, I am having an array, and the array contains the elements like 20, or maybe let's get started with a 70, then 50, 27, 99, 85, 47, 123, 34, 147. For example, this is the array that we have. So the starting index of this array will be 0, right? And it will go like this: 0, 1, 2, 3, 4, 5, 6, 7, and 8. Perfect. So this is the array that is given to us. Now what will happen? Here, if you will observe, suppose the starting index is something which is equals to P, and the ending index is something which is equals to Q. Starting index is P, ending index is Q. Now there are two variables that we have. One is called as I, whose major job is to, whose major initialization is with the value of P. And J is something which is equals to I plus 1. So these are the 2 pointers which are we have in a partition algorithm. So here I am explaining to you that how basically partition algorithm is working inside the QuickSort. And then I will tell you the algorithm of QuickSort as well. Okay. Now the question is that how division will happen? So what I am saying is that this is something, the very first element in our partition algorithm is something which we called as the pivot element. Now this pivot element is the fixed element which you can take as the first element, or you can take a last element, or you can take any random element. This is of your choice. As of now, I am considering that the pivot element is the first element, which is equals to 70, right? Now what we are trying to do is that you just need to take care that J is something whose major responsibility is to take those elements whose value is greater than this pivot element. If J encounters, so it will take the larger, or I would say greater than elements greater than the pivot. If it will getting it, if this J value, J index is getting this kind of element, it will moves on. And the duty of the I is to take the elements less than the pivot. Now, if suppose J will be getting some value which is having a value which is less than or equal to pivot, at that point of time, one thing will happen. So, if while doing the iteration, the error of J is getting some value which is less than or equal to the pivot element I am talking about, at that point of time, two things will happen. Now, because the responsibility of I is to take the smaller element of the pivot, so it will say to I that, okay, I will share with you the smaller element, but on the sake of that, you need to share to me the larger element. So what will happen? I will first of all get updated by one index, and then there will be a swap between the values present at array of I and the values present at array of J. This is the important thing which is happening while doing the iteration. Meaning, here if you will see, in the very first thing, the value of J is I plus 1. Now, this J is having a value which is lesser than the pivot. But the whole and sole responsibility of this J index is to take a value which is greater than pivot, then only it will move on. So now it will contact to I. I will update the value by 1 first, and then there will be a swap which will happen. Now, after doing the swap also, they will be at its own position because the value of I and the value of J is same. Now again it will move ahead. Again the value is lesser, so J will move ahead. The value of J, which it is getting by saying the value of J, I am saying the value of array of J. The value is somehow smaller than the value of the pivot element. Again it will contact to I. I will upgrade its position by I plus 1, and then again a swap will happen, right? It will go again next. Now what will happen? There is 99. Now this value is greater than the value of pivot. At this point of time, it will not do anything. It will simply move on. Similarly, again here if you will see, the value of 85 is somehow greater than the value of 70. So it will not do anything and it will simply move on. Now the value is 47. Again, this value is somewhere smaller than the pivot element. So first of all, it will connect to I. I will update the data or the index by 1, and then a swap will happen. Now what is the value of array of I? 99. What is the value of array of J? 47. So 99 will go here. 47 will go here. Correct? Now again the value will get updated. Again the value will get updated. Again here if you will see, the value is 123. Right? Now this value 123 is somehow greater, so nothing will happen. It will just move on. 34. If you will see here, the value is somehow lesser than 70. So now again it will connect with I will update its index, and then there will be a swap. 34 will come here and 85 will come here. And finally, it will go to the next position, and here if you will observe, the value of j is 147, the value of I is 70. So again here if you will observe, there is some way I can say a difference between the value, and the value of 147 is somehow greater than the pivot element, so nothing will happen and it will stop it here because it reaches towards the end of the array, right? Now, once it will be going out of the for loop, so here there is a for loop which will start from 0, right? And is moving until the value of n minus 1, can I say? So it will start from 0, or I would say the value of I, what we can say is that the value of I is equals to the value of p, which is the starting index, and here is a for loop for j, which will start from I plus 1, the next position, will go until the value of n, right? And it will be j plus plus. It's just a pseudocode. Please don't go with the exact syntax, right? So this is how things are working. Now when it will go out of this for loop, what will happen? One final swap will happen. That is the swap between the value of r of I and the value of r of p, which is the starting index, which I am considering as the pivot element. This is something which I am considering as the pivot element, can I say? So there is a swap between these two values. Means what is the value of r of p, which is 70. What is the value of r of I? It is 34. So 70 will go here and 34 will come here. Final swap will happen. Now, after the first iteration, how your array will look like? It will look like 34 followed by 50, 27, then we have 47, then we have 70, then we have 99, then we have 123, then we have 85, and after that we have 147. So this is the data that I will be able to get as a final thing. What was my pivot element? My pivot element was this. Indexes are 0, 1, 2, 3, 4, 5, 6, 7 and 8. So now, can I say that the pivot element reaches its own position after the first iteration? If you will see the final sorted array, what will be the output of yours as a final output? Your array should look like, I think 27, 34, 47, 50, 70, 85, 99, 123 and 147. So here if you will observe one thing, which is that at every iteration, whatsoever is your pivot element is, that will be reaching towards its own proper position. This is the final sorted array, right? Which you will be able to get at the end of your result. This is the final sorted array. But here you will observe that you are getting the same position here. If I will write the index number here, 0, 1, 2, 3, 4, 5, 6, 7 and 8. So one thing which you will observe here is that this 70 automatically reaches to its exact position, which will be there even after the complete sorting. That is the first thing, key thing to observe, right? Now, in the next important point, if you will observe all the elements which are left to the pivot after the first iteration, all the elements which are left to the pivot are somehow smaller than the pivot element. Can I say? All the elements on the left side of the pivot are the smaller ones, and all the elements which are at the right side of the pivot are the larger ones. So these are the elements which are, can I say, which are somehow larger than the pivot element, which are somehow larger than the pivot element. Can we say? So that is the key thing here. That is the key thing here. So here the elements at the left side will be less than the pivot element. Element at the right side will be greater than the pivot element. Now what will happen is that you will apply the same process of the quicksort on, suppose there is a function of quicksort, so there will be a recursive call which you will apply, right, on the index from 0 to 3, and on the right side again you will apply a recursive call which will start from 5 to 8, because this fourth index is at its own position. 70 is fine now. We need to do the same task towards the left side and towards the right side. So again there will be two recursive calls which will happen towards left and towards right. And the same partition process will again apply towards the left side of the part and towards the right side of the part. And this step will keep on moving. So majorly, what is happening here? So the simple pseudocode here is that majorly, if I will talk about the pseudocode of partition algorithm, so what we can say is that, suppose here we will be having a partition algo or the function where we will be having the complete array R, we will be having the starting index P and the ending index Q. So inside that we are taking one variable called I, whose value we are assigning as P, and then we are starting one for loop which will start from the value of I plus 1 and will go until the value of n minus 1. One more thing here is that before applying the for loop, we need to define the pivot element. So what is the pivot element? Now I am saying that pivot element will be anything, but here I am fixing the pivot element as the starting of my array element. Okay. Now we are applying one for loop which will start from the value of I plus 1 and will go until the value of n minus 1. Means until the end of the array, we are doing one simple traversal. Inside the traversal, because we know that the importance of j is to take an element which is greater than the pivot element. If that is the scenario, j value will keep on updating. But if suppose the responsibility of I is to take care of the value which is less than the pivot. So if suppose there is some value or the element which is having a value which is lesser than the pivot one, so first of all the value of I will get updated and then the swap will happen. So what will happen here is that if the value of R of j somehow is able to get a value which is less than or equal to the pivot element, what we need to do is that we need to first of all update the value of I, because j will connect with I, and j will demand that if I am giving you the smaller element, you should also give me the larger element. So that's why I will update its value by 1, and then a swap will happen between the value of R of I and the value of R of j. And finally, when we will be moving out of this for loop, what we are doing is that a final swap will happen between the value of R of, I would say I, and the value of R of P, which is nothing but is the pivot element in our array. Can we say? So this is the simplest pseudocode of a partitioning algorithm. And in this algorithm, finally what we will be able to return, we will be able to return the value of I. Can we say? We will be able to return the index of this 4, this value 4. So this partition algorithm will return me the value of m, which is the middle value, as 4. So that I will call the recursive function from the value of p to the value of m minus 1. And so here the quicksort will call from p to m minus 1. And here the quicksort will call from m plus 1 to the value of q. Correct? I hope I am making sense to everyone. So here this m is the index of the final I, right? So it will return the value of I. Now how the quicksort will work? What will be the pseudocode for a quicksort algorithm now? So what will be the pseudocode for a quicksort algorithm? So finally, we can say that what we are doing here is that we are applying a quicksort algo. Inside that, we are passing the value of R. We are passing the value of starting index P and the ending index Q. Again, we can say that if the value of P is less than Q, right? Until that point of time, we are finding out that mid value. Now we are not finding out that mid value by applying P plus Q minus P by 2. No. Here we are applying a partition algorithm. That algorithm we already have talked about, which will take the value of R, P and the value of Q. And after that, we will again call the quicksort algorithm for the left side and the right side recursion. So R of P and until the value of M minus 1, as I already talked about the same. So here again, the recursion will happen. And on the right side again, the quicksort of R M plus 1 until the value of Q. So this is for the, I would say, left side recursion. And this is for the, I would say, right side recursion. Right side recursion. Right? Left side and the right side recursion which is happening. So here if you will see, this is the dividing part. Right? This is something which we can say is the conquering part. This is something which we can say is the conquering part. And because the partition we are doing very smartly, so there is no need of combine part in the quicksort algorithm. That's why it is way smarter. So in this quicksort algo, we don't require the need of a combined part because the partitioning that we are doing is in a very apt manner. Okay, perfect. I hope that I'm making sense to everyone. So basically what will happen is that suppose we will be having an elements from 0 to 8. So what will happen is that a quicksort will be called, right? A quicksort will be called where the value of R is this from 0 to 8. Now partition function will simply give me the value, return will me the value of I, which in this case we are getting as 4. Now it depends on the kind of array that you have. It will not be always the middle value because here the process of dividing the array into two halves is completely different. Correct? So here now if you will observe, you are getting as of now 4. So you will call, because the value of M or the mid you are getting as 4 by applying a partitioning algorithm in the first iteration. What will happen? Quicksort from R0 to 3 will applicable here. And on the right side you will call quicksort of R from 5, which will be M plus 1 to 8 will be called here. Now again you will try to solve this left side from 0 to 3. So if I will try to solve this 34, 50, 27 and 47, right? So on the left side we will be having 34, 50 and then we have 27 and 47, right? 27 and 47. So it will be 0, 1, 2 and 3. Again this is the value of P, right? This is the value of I and this is the value of J. So now again what will happen? Always remember, this is the pivot element that we have. 34 is the pivot element. Now J responsibility is to take a larger element as comparable to the pivot element. If it is larger, it will simply move on. So 50 is greater, it will simply move on. Now 27 is coming up. It is smaller. So what will happen? First of all, I will get updated. Then there will be a swap. 27 will go here. 50 will come here. Now J will update it. Now in this particular case, the value 47 is greater than 34. So nothing will happen. And it will get stopped. Finally, there will be a swap between the value of the pivot element and the value of array of I. So 34 will come here and 27 will go here. So finally, after applying the recursive call in this part of your array, you will be able to get the value as 27, 34, 50 and 47. And finally, your value of I is something which is equals to 0, 1, 2 and 3. So the value of M is something which is equals to 1. And here if you will observe, this pivot element 34 in its actual array, sorted array, will also be its own position, just like the 70 I was talking about. So always remember, whatsoever the pivot element you are getting, after completion of the iteration, that will be located at its own position. So now here if you will observe, the value of I will be returned, so value of M will become 1. So now again, for this particular array, again the quicksort will be applied towards the left and the right side of the array. So now what will happen? The left side will be again the function call quicksort from 0 to, so it will take the complete array R, starting index 0, ending index will be M minus 1. So it will be 0 only. That's why you will be having only single element. On the right side, you will be having quicksort from M plus 1, which will be equals to 2 to 3. And now this is something where you will be having only single element 27. It's a small problem. So it will simply return the value as 27 only. Now it will go to this particular part where you will be having the array element 50, 47. Now again what will happen? This is P, this is Q, this is I. This is the pivot element, right? Now again, here it is J. The value is smaller. If the value is smaller, I will get updated. There will be a swap. Position will remain same. So now final swap will be between pivot and the value of array of I. So 50 will be here, 47 will be here. And finally the value, it will return is, the index is 1. So here the value of M will be returned as 1 only, right? Not 1, what is the actual index? It is, I think, 2 and 3. Sorry, so the index was 2 and 3. So here it will return the value as 3. So the value of M is equals to 3, right? Now again what will happen? The function call will happen. So here the value is 47 and 50. So again quicksort of 2 to M minus 1, 2 and quicksort of M plus 1, which is 3 to 3. Again it's a small problem. So it will simply return the values as 47 and here it will be 50, right? So here finally we will be able to get the values as 47, 50, correct? Here it was 27. Now it will go up, 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 so on. So finally here we will be able to get the value 27 followed by 34 followed by 47 followed by 50, right? Which is actually a sorted array itself. Again, the same recursive tree you can draw here as well. I'm not doing, I'm leaving for you. You can try to observe the pattern and just complete this right portion of the recursive tree. So this is something that we have as a recursive tree of a QuickSort algorithm, right? This is something which we can say is a recursive tree of a QuickSort algorithm. Now, the final thing is the talk about a recurrence relation, which is really important for a quicksort discussion. Recurrence relation, which I want to talk about here. Now try to understand, because in the recurrence relation, various students I have seen goes wrong with respect to the quicksort algorithm. Here if you will observe, whenever I am talking about partitioning algorithm, what do you think should be the time complexity? Here we are just using one single for loop, which is starting from I plus 1 and moving until the value of n minus 1. So in worst case scenario, can I say that this time complexity will be n only? So big O of n, can we say? This is the time complexity for the partitioning algorithm. Now, talking about this part of the first iteration, the value will be t of how many number of elements do we have? Now here you can't directly write it as n by 2, because you are not sure that the elements that you are getting or the value of mid that you are getting will be at the middle only, right? So here it is something, you can write it as m only, right? Because we are using m and m here. So you cannot write like this, meaning what I want to say here is that it might be the case that the value of m, for example, you will be having an array like this, 27, 19, okay? Then you will be having 49, 57, 29, 46, 37, and so on. Now here this is the pivot element, right? Once you do the iteration, first iteration, we all know that after doing the first iteration, 27 will be at the second position and all the elements on the left of the 27 will be at the smaller side, right? All the elements left of 27 will be smaller, and I'm just randomly writing the numbers. I'm not sure the sequence will be correct or not, but this is what I'm sure is that the elements towards the right side of 27 will be larger. So here in this case, the value of I is something which you are getting as 1. This is the index 0, 1, 2, 3, 4, 5, 6. So here the value of I that you're getting is 1. Can I say? Means this will return the value of m as 1 only, right? Okay. So what I'm saying is that this is not the middle value. So here if you will see, you are not having the numbers n by 2 on the left side and n by 2 on the right side. You are having almost all the numbers on the right side itself. So you can't write the recurrence relation like the way we used to write in our binary search or in our merge sort. We can't write like this, n by 2, because we don't know that half of the elements will definitely be at the left side and half of the elements will definitely be at the right side. So at that point of time, you need to calculate how many number of elements do we have for the left side. It will be m minus 1 minus, so m minus 1 is the last index, minus p minus 1, right? So it is something, and here it will be q minus m plus 1. So it will be m minus 1 minus 1. So basically, if I will talk about in an approximate manner, it will be m minus p, it will be q minus m. Can I say? So that's what you need to understand here. So m minus 1 minus p plus 1. What was the formula to calculate the number of elements? Just now, few minutes back, I have talked about what is the higher index minus the lower index plus 1. So m minus 1 minus p plus 1. So this will be m minus p. Higher index is q minus lower index is m minus 1 plus 1, which is equals to q minus n. So what can I say is that the number of elements present at the left subarray is m minus p. Number of elements present at the right subarray is q minus m. So what can I say is that the recurrence relation will be T of n, where when the value of n is equals to 1, means we will be having a single element, then it will be a constant quantity, right? This will take a constant time. But when the value of n is greater than 1, at that point of time it will be T of, I think, m minus p plus T of q minus m plus the value of c. Sorry, the value of n. Partition algorithm is taking the value as n. M minus p and q minus m, right? Perfect. So this is the recurrence relation of the QuickSort that we have, right? Of the QuickSort that we have. Now you need to understand here, what will be the best case scenario here in this recurrence relation? What will be the best case scenario? The best case scenario will be when half of the element will be present at the left side and half of the element will be present at the right side of your pivot element. For example, the question that we have solved right now, just now, where almost 4 elements on the left side and 4 elements on the right side. So there will be not much burden on either side. Almost equal elements are there on the left and the right side. That is the best case scenario. What will be the worst case scenario? Just like the example I have discussed here, where almost all the elements are at the right side or at the left side. For example, in this case, you will see almost all the elements are at the right side of the pivot element. There is only single element which is left on the left side. And vice versa can also happen. Means all the elements will be at the left side, or maybe there is no element, or maybe single element will be present at the right side of the pivot element. So when I'm talking about a best case scenario, it will be something where your recurrence relation will be equals to left subarray will contain half of the elements and the right subarray will contain half of the elements plus n. So if I will solve this, it will be 2tn by 2 plus n. If you will remember, this is the recurrence relation. We got the same recurrence relation for the merge sort as well. And if you will try to solve this recurrence relation using either the Master's theorem or by applying a substitution method, I'm not solving it. I think I have solved already a lot of times the same thing. You will be able to get the value of t of n as big O of n log n. Right? You will be able to get this time complexity. This is the best case scenario. But what will be the worst case scenario? What will be the worst case scenario? As I told you, worst case scenario signifies that the value of t of n is something which is equals to t of n minus 1, where it indicates that all the n minus 1 elements are on the one side. Only single element, which is a constant quantity, will be at the left side, right? All the n minus 1 elements are at the right side plus n. And if you will try to solve this recurrence relation, it will be something coming out to be big O of n square. Right? This is something which will be coming out if you will try to solve it using a substitution method. It will come out as big O of n square. What I want to say here is that when you are solving any question using the QuickSort algorithm, there are chances. Okay, what will be the average case? Average case will be half of the time you are getting a best case scenario. Maybe it's quite significant low chances that you are getting a worst case scenario. I will talk about the same, that at what instant of time basically this worst case scenario will come. I will talk about that. But in a nutshell, when you are talking about a best case scenario or the average case scenario, best or the average case scenario, you are getting a time complexity of big O of n log n. But in the same QuickSort algorithm, when you are reaching towards the worst case scenario, which we will do a great talk about the same, I will show you that when this worst case scenario will happen, at that point of time, that same algorithm can tend to big O of n square as the time complexity. So that is what you need to make sure. Basically, this worst case scenario will happen whenever your array is almost or fully sorted. At that point of time, you will always encounter this worst case scenario. That's why, if you remember, at the starting of the session itself, I told you that always go for this quick sort whenever your array is highly unsorted. Array is highly unsorted. At that point of time, it will for sure give you a good result with a good time complexity as well. And it will give you very fast, because here there is no combined process. Here is just partition process which is going on and which will take a few minutes of time. Few seconds, I would say. So here, if you will see, when the array is highly unsorted, always go for quick sort. When the array is almost or fully sorted, never ever go for quick sort. It would be better when this kind of scenario will happen, you should go for the insertion sort. At the time of the session in the insertion sort, I already had a talk about that thing, that insertion sort will give us, in that case, big O of n time complexity, which is way faster as comparable to quick sort or the merge sort, right? So these are the scenarios, and depending upon the scenario, you should know that which particular sorting algorithm you should go for, right? Why I am saying that in the worst case scenario, when the array is fully sorted or the almost sorted, you are getting big O of n square, or you are getting a worst case scenario, because here if you will see, for example, I am having an element like 10, 20, 30, 40, 50, and then 5 is there. This is the array which can I say is the almost sorted array, right? Almost sorted array. Here if you will observe, what will happen? In this case, it will be 0, it will be 1, it will be 2, it will be 3, it will be 4, it will be 5. This is P, this is I, and this is J. Now, this J is getting the value which is greater than the pivot. It will move ahead, again it will move ahead, again it will move ahead. Again, if it will reach here, at that point of time, the value 5 is lesser than the value of 10. So the value of I will get upgraded, and then there will be a swap. 20 will go here and 5 will come here. Can I say? 20 will go here and 5 will come here, and once it will be out of the for loop, the value of pivot and the value of A of I will get swapped. So 10 will come here and 5 will come here. Finally, you will be able to get an array which is 5, 10, 30, 40, 50 and 20. Can I say? So at this point of time, it will return me the value of I as 2, because the value of I is 2 and we are returning the I value itself. So it will simply return me the value of M, which is the mid value, as 2. Not 2, it will be 1, sorry, 1, right? Because it is at the first index, so it will be 1. So it will return me the value as 1, right? 0, 1, 2, 3, 4 and 5. So it will return me the value as 1. So now I need to apply a QuickSort algorithm towards the left side of M, which will be AR starting index is 0 and ending index is 0, means on this part. And on the right side, these many elements are there. QuickSort, complete array AR. Starting index will be M plus 1, which will be 2. And the ending index will be Q, which is 5. So you can see that almost all the elements will be at the right side of 10, which was the pivot element that we have, and the smaller element, which is only 5, will be at the left side of 10, which is highly biased situation, right? This is something which I was talking about, the worst case scenario in a QuickSort. This is something which I am talking about, a worst case scenario in specifically talking about QuickSort, where you will be able to get the time complexity as big O of n square. Correct? So that is something which you need to take care of. That's why I am saying that when the array is fully sorted or almost sorted, never ever go for QuickSort algorithm. Always go for insertion sort kind of algorithm where the time complexity is big O of n, right? So in this particular session, overall, we did a great in-depth discussion about the QuickSort. We started with the partition algorithm understanding. After that, we have seen the pseudocode of the partition algorithm followed by the QuickSort algorithm. After that, we have seen the recursive tree for the same, because the recursion is applicable here. And because there is a recursion, there will be a recurrence relation as well. So in this recurrence relation, we have a great talk about what will be the best case and the worst case scenario for the QuickSort algorithm and when will it happen. So best case will happen when the array is highly unsorted, and the worst case will happen when the array is highly sorted, right? One last thing which I want to convey in this session before closing it is that when we talk about QuickSort, it is an in-place algorithm, right? Because in all of our conversation, as a key point to note, I would say at the end of the session, I want to say few points about QuickSort. Very first point is that it is an in-place algorithm, because as you can see at any part of my session which I am teaching here in the QuickSort explanation, never ever I said that we are using some sort of extra space, just like in a merge sort I talk about, right? So the very first thing that you need to understand is that it's an in-place algorithm, or you can say in-place sorting algorithm. It's an in-place sorting algorithm. Can I say? The second important thing here to understand is that it's not stable algorithm. Until so far, we have seen only a stable algorithm. But this is something which is not a stable algorithm. I have already talked about the meaning of the same. Apart from this algorithm, which is the QuickSort, the heap sort is also not a stable algorithm. Why? Why is that so? Because here, just try at your home. I'm giving you as an assignment. Suppose I am having a value which is 10, 10, 10, 10, 10. Now, obviously, it is same numbers. For example, 10, 1, 10, 2, 10, 3, 10, 4, 10, 5. Just for your distinguishment, you can write it like this. Try to apply the partition algorithm here. So what stable algorithm says? It says that after doing the sorting, after applying the QuickSort algorithm, pattern will remain same. For example, 10.1 is coming first, so it should come first, 10.2 should come second, 10.3 should come third, 10.4 should come 5, 10.5 should come at the very end. But do let me know that after applying the QuickSort algorithm, by applying a partitioning algorithm, is this pattern is retained or not? You will observe that this pattern or the sequence of the numbers that we are getting is not retained. And that is what where we can say is that it's not a stable algorithm. So you will observe that sequence is not retained. That's why it is not a stable algorithm, but it's an in-place sorting algorithm. That's a good thing, means we are not using any sort of extra space to implement that, right? This is the another key thing. And last important thing is that this particular algorithm is widely used in real-time scenarios, because it is a faster algorithm as comparable to merge sort, because it is not using any sort of combined procedure, just like the merge procedure that we have studied in our merge sort class, right? But only when our array is highly unsorted, only when actually the array is unsorted. That is the key thing to understand. Actually, the array is unsorted. So I hope that I am making sense to everyone. And with this, the complete explanation of the QuickSort algorithm is completed by my end. If you still have any sort of doubt, you can let me know, right? I'll try to resolve it as soon as possible. And with this, happy learning to all. In our next upcoming session, we will try to discuss the implementation for the same. And before watching that session, it's my humble request to everyone that you can try to run your code at your end, because I have already written in a very clear manner what is the pseudocode for the QuickSort as well as for the partition algorithm. So whichever programming language you are comfortable with, start writing the code now, because you already have understood the internally in-depth explanation of the QuickSort algorithm, right? First of all, understanding of concept is important. Secondly, doing the implementation is also equally important. So with this note, I would like to end this particular session. I'll see you all in my next upcoming video. Bye-bye everyone. Take care and happy learning to all.